Okay, welcome back. This is part 2 of 2.1.7 number 4. And by popular demand, by requests from some of my YouTube followers, I am going to get this video out as quick as I can. I know the suspense is building and people want to know what happened to the end of this problem. So let's get started. The first thing we're doing, we should probably review quick. Part 1 was looking at external forces and the fact that we needed to know what those reactions were at our pin and our roller. So we will be using that information to find our internal forces. And again, reviewing internal forces are the forces that are actually felt by each member of the truss. So picturing this, you could imagine that the 50 pounds is going to put some strain on potentially all 3 members. Maybe not, and I guess we'll find out here in the end. But the amount of force per member is not necessarily the same. It's not like we divide the total force by the number of joints or the number of members. It's much more complex than that. So we are using the method of joints, and that just means that after we find the external loads and the external forces, we go to each joint one at a time, and we analyze a free body diagram at that joint. And for our purposes, we typically we start the method of joints by using the pin joint to start. So with that methodology in place, we will start at method of joints at point B. So you can see I already did the free body diagrams for us just to save some time. And it's the same free body diagram written 2 different ways. So the one on the left here, the point B is the dot. Now, we already know we have the reaction force B in the y direction. We know we have the reaction force B in the x direction. On top of that, in the internal loading, we have member AB may be feeling some forces. And then we also have member BC, and we draw those at the appropriate angles. We did talk about how when we do method of joints, we assume members are in tension. And so real quick, when we have a member that is maybe fixed here, to feel tension means that we're trying to pull the member apart. We're trying to stretch it out. So again, the reaction force of that is going to be represented by an arrow that points away from the joint. Okay, so these are the forces that I'm scribbling out the actual tension force. So the forces we draw in the free body diagram are represented by the arrows pointing away from the joint or towards the middle of the member to show tension. So that's why we have AB and BC pointed away from the joint. That is assuming tension. So let's see if I can find how my pen works. There we go. The other way to write this is breaking this down into just x and y components, which is why we did 2.1.3, where we did vector forces, or force vectors, I think we call them. And the reason we did that was it's really hard to figure out what member BC is feeling when we look at it at a 45-degree angle. Instead, we break it down in this free body diagram as the RBX, RBY, and member AB is all vertical, but BC can be seen as not just BC, but rather BC in the X direction, BC in the Y direction. And you'll see how that's going to come into play here soon. So we don't do summation of the moments at this point. We just jump right into summing the forces in the X and Y direction. So with that said, however, we got to pick. Are we going to do X first, or are we going to do Y first? Well, if I were to maybe change this pen setting real quickly, I'm going to turn it yellow. So we know RB in the X. We found that previously. And we also knew RB in the Y. So we have those 2 forces solved from doing the external loading. What we don't have is everything else. So when you look at this, the problem is going to be if we were to sum the forces in the y direction, we have two unknowns. So one equation, two unknowns, not going to work. If we look in the x direction, however, we only have one unknown. We have BC in the x direction, and that's it. So with that in mind, we're going to go ahead and solve the sum of the forces in the x direction. And again, we know that we don't want this bridge moving. We want it to go in the x direction at 0 pounds. So let's look at our two forces we have. The RB in the x direction is one of them. Now, RB in the x direction, that would be a negative because, again, our arrows do have meaning. So pointing left, traditional method, left is negative, down is negative. Plus, we have BC in the x. And we know 0 equals negative 50. So negative RB in the x, if you were to go back and look, we found the reaction force to be 50. So we know that BC, just in the x direction, is 50 pounds. That's great. Okay, we have BC in the x. What do we do with it? Well, we need to use that so that we can find BC itself. So let's look at that as broken down into, we have, here's BC itself, right? And we have BC in the x and the y. Well, I said that backwards, but BC in the y, BC in the x. So here's BC in the x, here's BC in the y. There's our 45. And that 45, again, we have 3 feet x, 3 feet y. That's where we're coming up with that 45 degrees. Now, if we know that BC in the x is 50, we have a triangle that we know one angle, its opposite side, and we're looking for the hypotenuse BC. So if we write that in a trig form, we say the sine of 45 degrees is the opposite over hypotenuse. Now if we rearrange this, we multiply both sides by BC, divide both sides by sine of 45, we run our magic wand over it, we find that BC is 50 divided by sine of 45, or that just comes out to 70.71, something like that, pounds. So BC is 70.71 pounds. When we did this, note that the BC in the x was positive. If you think about what did that mean, remember if we found that our answer was negative, that had meaning. If we find it positive, that also has meaning, but since we found it positive, that means that we assumed the tension correctly. So that means that this member BC is in tension. So I'm just going to summarize. So BC is 70.71 pounds. I'm also going to write that up here. BC 70.71 pounds. And then check this out. I'm going to change that. I'm going to change the color. Ooh. Crap, can't do that. See if I can do it again. It worked last time. Oh. So it did work. Okay. So we can fill that in, and as we do these, we're filling them in as we can get them. So now I'm going to use a little bit of background knowledge in trigonometry and solve BC and the y here. We know that at a 45 degree, both legs of the triangle are the same. So we're going to say that that's also 50 pounds. That's going to come in handy because we will also do some of the forces in the y direction. We know that those are 0. Well, let's go back now and see what we know. Well, we have R, not an R. That's an R there. RB in the y direction, that's pointing up. minus member AB minus member BC in the y direction. So that said, we fill in what we know. Okay, so 0 equals RB in the y direction, again, going back to our external forces, that was 50, minus AB minus BC in the y. BC in the y is 50. So 50 minus AB minus 50, so 50 minus 50, 0 equals negative AB. Well, 0 isn't positive or negative. I mean, you could argue, mythical hypotheticals here, but for our purposes, we're just going to say, you know what, AB is 0 pounds. So we're going to go AB, that is 0 pounds. And you know what, I forgot to add the T. Remember, we always put these in tension or compression. We assumed correctly on BC. Did not mean to erase that. It really hates me now. Okay. I will get these changed to the right color, I promise. There. I don't know why it doesn't want to circle that. Okay, well, we'll leave that for now. Anyways, my point being here, AB, member AB is a zero force member is what we call that. And what it's saying is all the force applied from AC, which we haven't even figured out yet, is pushing on A in the x direction, which means there's no vertical component. Same thing with B, because that's a pin joint, it's saying that we're not going to feel any force in member AB. So 12 minutes, I've taken too much of your time. I'll clean that AB up here in a second. And while I do that, what you're going to find is that we need a third video to get through all of this force stuff. So 0 pounds. I will not put tension or compression because there is no force, so it's neither. So with that said, thank you, followers. I will get you part 3. I don't know, that's a lot to ask for one day, getting 3 videos out. But again, remember to smash that like button, follow me, and I promise I'll get you some more videos out here soon.